All right. Now we're back in business. Appreciate that. Yeah, so I was just saying that essentially the lead of the team that does El Nino monitoring and predictions, I'm often asked the question, why do you use an index for this very multifaceted, complex system? And the response to that simply is that we have this user requirement, and users are driven towards simplicity. They want a very clear thresholds in an index that's simple to calculate, and they want to be able to trust it. And part of trusting it is being able to understand how it works. And now there's a long history of these users using our primary indices. But that is obviously in tension with the science and the complexity of the system. So I'm a little bit of the person in between, trying to navigate that. I sometimes describe myself as a middle manager for ENSO. So basically, no one likes me. But I do take this responsibility very seriously, and I want to make as many people happy as possible. And so, in looking at this index, we want it to do an adequate job most of the time representing the ENSO system. And what we've noticed in recent years is that we're starting to see new features that suggests that the non-stationarity in climate is impacting our primary index. And we need to investigate that and address it. So before progressing here, I want to emphasize there is a large team of scientists behind this work. I am certainly not the person who invented this. I'm helping push it along, especially from the applications perspective. But there is two papers here. The first one is Gert-Jan von Oldenburg, who passed away several years ago. He really spearheaded this in collaboration with Harry Hendon, who's now retired. And they came together and realized, we have a real issue here of our ENSO index and the fact that there's the changing climate. So how can we address it? And they came up with the relative SST paradigm, which drew from even older work, especially in the tropical cyclone community, which use relative SSTs to understand convective instability. So that paper down there in the lower right was published early to 2024. And that arose because we were in collaboration with Bureau of Meteorology in Australia, and they were also noticing this non-stationary climate and realizing that there's some serious offsets here. So we put our heads together and we collaborated on that paper. It's just a little bit more applications focused in studying this issue. So I recognize not everyone in this room is an El Niño-Southern Oscillation expert, and I hear you, and I just want to go quickly through some of the terms I'm going to be using over and over. And so primarily, there's definitely different ways to measure this, but primarily we measure it as a departure from average in sea surface temperatures in the central and eastern equatorial Pacific Ocean. El Nino is above average, La Nina is below average. And I'm emphasizing that word average because for this talk is really important what you consider the average to be. And so we have to use a reference period, a base period. I use all of these things interchangeably, climatology. And this is mandated also by the National Weather Service, which is where CPC is housed. They use a 30-year climatology, which is recommended by the World Meteorological Organization. They update this every 10 years. In this talk, I'm going to be emphasizing the NOAA definition. This is very important because no center around the world defines it exactly as we do. There's a lot of different ways to do this, different thresholds, and different points of emphasis. If you're in Peru and Ecuador, you care a lot about coastal El Nino events. So you do need your own separate and unique definitions in order to capture those events. And so in the NOAA definition, we say 5 consecutive overlapping seasons. What I mean by seasons is a 3-month running average. And that Nino 3.4 region, which is in the east central tropical Pacific here. And and this is the time series that emerges when you average sea surface temperature anomalies. The reds here are our El Nino events, the blues is our La Nina events. And I sometimes use Nino 3.4 index and oceanic Nino index interchangeably, but that's not quite right. Nino 3.4, I usually use in reference to weekly and monthly averages. The oceanic Nino index is the 3-month running average through the time series. So it's a more smooth version of this, which does get at that coupled variability. So I sometimes say ONI when I'm referring to that 3-month running average. Okay, now that we have that out of the way, let's get to our problem and why we're here today, which is the classification of El Nino, La Nina events will change depending on your base period or your climatology. And on the left there is our time series. It goes back to 1950 up through the present, and it shows the ONI. And this is using a 1991-2020 climatology. You see your distinctive El Nino and La Nina events, often multi-year here, a little more in duration. You see the asymmetry. The El Nino peaks tend to be a little greater than La Nina peaks. So you see all these features. Now look, this same time series, except instead we're going to be using an older climatology. This is 1941, 1970 climatology. And here we have similar features, except these two time series look pretty different. In particular, in the more recent record, you have more and stronger El Nino events, and you have fewer and weaker La Nina events, right? So what this means is, depending on which climatology you pick, you know, your basically your El Nino La Nina events will change. All right. So this is a little problematic because, we don't want to be living in the 1950s and experiencing a La Nina that is defined on a climate that occurred up to 70 years later. That makes no sense. All right. That wasn't the climate at the time in the 50s. So why are we doing this? So why is this happening? All right. Very simple answer here. Climate is warming. This is showing the seasonal cycle, total sea surface temperatures in the Nino 3.4 region. I'm showing this in ERSST. This is the data set that we rely on as CPC because it's NOAA, it's updated in real time, but we have also done this analysis in other SST data sets, and it looks like this: HAD SST, COBE SSTs. So the actual, specific features might change a little bit. You'll note right away that the climate is not warming uniformly. There's these jumps. I should back up and say that our older climate is the red colored lines, and our newer climate here is the blue colored lines. And so what we see is that there are these jumps. This is definitely not monotonic. There's differences based on the time of the year. But in the net, it's warming. So one goal, too bad that got blocked, but one goal of this relative SST index is to define our El Nino and La Nina events, irrespective of the climatology you pick. How do we do this currently? So right now in operations, we do not use a relative ONI as our official index. So how are we doing this right now? Because we did recognize about a decade ago that we had this non-stationarity, and we knew, we have a problem here. And that problem is illustrated by this top plot, which is the ONI. The red line is using a fixed 1991-2020 climatology. And the green line is the method that we settled on in operations, which was to use a centered 30-year climatology that moved through the record. And so our current operational version at CBC is the green line. And you can see that difference if you use that climatology, just single climatology through the entire record. There's a big jump here. And in fact, this is the difference plot you see at the bottom. And you get these little unphysical jumps every time we update the climatology. We do this every 5 years. We don't like 10 years is a long time, so do it every 5. But regardless, this doesn't look great. It's really, really not ideal. So, and this is just complicated, all right? Every time I explain this, I'm like, why do we have to do it like this? For historical ONI values, we use the centered 30-year climatology. For real-time values, we can't center it. We don't have the future. So we have to lag the climatology. So this is the only period that we officially measure at CPC. And you can see the 30-year base period removal in our historical record, and that gets updated up to a point. All right, so our most recent CLIMO is 1991-2020, and we use that for all these periods in here. So basically, this will be permanently fixed. The ONI values between 2006 and 2010 will be fixed at this CLIMO, but all these other periods will eventually have their climatologies updated. And so this, as you can imagine, gets very awkward. We have this big table of El Nino, La Nina values at CPC. We color code it so you can see the La Ninas and the El Ninos. Right now, we're in a cool state that we're calling La Nina conditions. And I had a colleague at a CPC who noted, he was like, wow, I mean, if this is the first value of our La Nina occurring in November, December, January, this is the latest one we've seen in the whole 1950 onwards record. And I pointed out, well, kind of, because the reality is this value that we have in real time will change every time we update the climatology. All right. And based on this, we actually don't know exactly when the start is. In fact, I'm willing to wager that we will see it start actually even earlier, at least OND, which point it is not the latest La Nina on record, when we arrive at our fixed full centered 30-year climatology. Anyway, isn't this annoying? Yeah, so we've had this problem for a while, and that's why when Gert Jan von Oldenburg came to me with this relative SST, I was like, oh my God, thank you. Because this really does help us get around some of these issues. So let me explain. So this is what the time series looks like. Our traditional ONI is in red here. Our relative ONI is in blue. And one thing I want you to immediately come away with is that these are really similar time series, all right? For our users, this is not a huge change because it looks very similar. We still have our El Nino variability, we have our La Nina variability. The index, the statistics are largely the same. Except, and I'm going to bring your attention to the most recent record in the last 10 years or so. That red line, the traditional ONI, has almost been uniformly above the blue line and the relative ONI. All right. And so this presents a bit of an issue. Here we go. All right. So now I'm going to give you kind of the agenda of the talk. And I'm going to structure the rest of the talk by this. So we've already kind of gone over point number one, which is that a relative Nino 3.4 index is pretty similar to the traditional index, and users can use this almost exactly the same way. And this is what I call the do no harm principle. We're not wildly changing the statistics of our ENSO index on our users. The second advantage to using this, and this is honestly one of the most magical parts of this, is that you can use a single 30-year climatology. It doesn't really matter which one. And you will still consistently identify El Nino and La Nina events in your record that are roughly the same. And I love this because I hate describing those rolling climatologies. It's really, quite frankly, the bane of my existence. So the third reason is important because why does that work? Why is the relative index even why is it able to do this? Well, it's because it's physically based. One thing to keep in mind is 30-year climatologies are a bit of a human construction. There's nothing special about 30 years for ENSO. I mean, you do want a climatology long enough to get to the statistics of ENSO and also have a long enough historical record. There's nothing special about 30 years, at least with respect to ENSO. And also this method, which I'm going to present in the next slide, does not require a lot of choices. All right. And I think it's simple and it's useful because in part, you don't have to do make a lot of decisions here. Over the hindcast record, we find the scale is roughly the same, which is good. We're not seeing a huge loss in skill. In fact, I would say in the last 10 years or so, we're starting to see an offset in error. And by error, I mean the forecast minus the observations. We're starting to see some increasing errors that I think could be attributed to these growing offsets. Finally, and this is more of a concern. So I think we published that paper in January of 2024. And since then, it's been remarkable to watch how these differences have really grown and emerged. I mean, they're quite concerning at this point. I think they're large enough that they're impacting the product in a way that's very noticeable to our users. All right, so I'm going to start with bullet point 2 here, and we're going to talk a little bit more about these climatologies. Okay, this is the Oceanic Nino Index. Both panels, you saw this before. This was in an earlier slide. On the left is the 1991-2020 climatology. On the right is 1941-1970 climatology. You're already kind of familiar with this sort of jump that we see when you go from a warmer to a cooler climatology. And so again, these differences are visible. You can really see the shift. All right, let's look at the same time series, but in relative space. Here it is. All right. And so here I'm using a 1991-20 climatology in the relative SSTs. And here I'm using the older climatology on the right-hand side here. And what you'll immediately notice when you sit here and study these two plots side by side is that they're more similar to each other, especially compared up here. All right. So you see a lot of differences here, but here you see general similarity. It's not perfect, but it's close. Another way to show this, I almost want to apologize for this diagram. There's a lot coming up here. Is this diagram. So this is like my mega plot, and I swear it's the same information you're seeing here, except now I'm doing like kind of a heat map perspective where the blues are the La Niñas and the red are the El Niños using that NOAA definition. And this is time, starts in 1950 all the way up to the present. And then here are different 30-year climatologies that I'm applying to the whole record. So I'm using a single 30-year climatology, and I'm seeing, where the La Niñas are and the El Niños are. So as one might expect, if you're using a cooler climatology like the one in 1930, 1960, you see generally warmer anomalies. You see more El Niños, they're longer, they're more obvious. And then when you look at a recent climatology, you're using a warmer climatology, you see more blues, especially in the past record. All right, so you see this clear difference. There's not a lot of vertical orientation here. You see almost these like fatter reds to the bottom, and then more of these blues towards top. This is problematic. This is the relative, so same perspective. And what's nice here is you really don't see like all the reds down here and then all the blues up here. If anything, you see a little bit more vertical alignment, especially as you get into these more modern climatologies. I mean, the reality is we're using some climatologies here that predate that the uncertainty in the ERC starts blowing up around World War II and so on. So there's probably a lot more uncertainty in this earlier part of the record. But if you get in a more recent part of the record, you start seeing these almost straight vertical alignments. And also interesting is that, and this updates through the November, December, January season that we just had, we're already in a La Nina. When we look at our NOAA criteria for relative, we're already there. Whereas when you look at the traditional, not so much. We haven't even qualified yet in that 5 consecutive seasons. Okay, so one of the reasons that we may see more consistency in the relative SST is because of the physics. And full disclosure, I did not come up with this, but it's a simple method, and it's something that you too can calculate. So what we're doing here to calculate the relative index is we're taking the Nino 3.4 index as we typically define it, and then we subtract out the tropical mean SST anomaly index. We're using a 20 north, 20 south band. You can play around with this. It won't change the answer too much if you go a little bit north and south. And so we take both of these. They both have a climatology removed, but you don't have to use the rolling climatology, so you just use one. And so you take those two indices and you subtract them, and you get this bottom index, which is the relative index. And now, because you've subtracted off, there's some ENSO embedded in here. And because you've subtracted that off, you lose some of the variance. And again, because we're using these thresholds that our users are very familiar with, we want to rescale this index so the thresholds remain valid and understandable and meaningful to them. And so the calculation is very simple. Again, it's just the ONI minus tropical average. And then we do this sort of inflation adjustment where we use the ratio, standard deviation of the traditional ONI minus standard deviation of the difference. All right, so we're just rescaling it. And you do that as a function of season. At the end, I'm going to show you GitHub link, which does this calculation in Python. And it's a short piece of code. All right, what's the physical basis? So the real experts are down here: Adam Sobel, Nat Johnson, Sheping Shea, and many others, particularly in tropical cyclone community, came up with the relative SST concept. And the general idea is that the tropics is a special place. We're actually kind of lucky, and so is in the tropics, because instability and precipitation and rainfall really depends on the difference between your local surface, sea surface temperature anomalies and the tropical mean. All right, so when you have, as many meteorologists know, it's cooler aloft and warmer near the surface, so you get convective instability. When it's reversed, you're more stable. And the reason this works is because we have this strong SST precip relationship in the tropics. And that is unique to it because there's a lack of Coriolis. And so fairly quickly, not within a day, but within like a month, you pretty much see the tropical mean temperature smooth out over the whole tropics. And so basically that means you can use the global, and the other thing is you can use global tropical SST anomalies as a proxy for free tropospherics. By that, I mean above the boundary layer. It follows the moist adiabat, as others have shown. Rainy region SSTs is nearly equal to tropical mean. I almost think this is magical, but this is one of the reasons this all works. And then, so basically the bottom line is local SSTs can change rainfall, but only when they're above that threshold, which can be estimated by the tropical mean SSTs. And if you have more questions, I definitely refer you to these references at the bottom. They go really into the theory of this. But this is physically based, guys. This isn't just something we're making up here. Fourth, over the hindcast record. So at CPC, we need to have uniformity between our monitoring product and our forecast product. We can't have different monitoring from our forecasts because then people get confused. We also can't hand wave things. We can't just say, oh, it kind of looks like El Nino. I'm looking at this, I'm looking at that, and so on. We need to measure an index so we can go back and verify. All right, we're not just playing around here. We want to make sure that we can actually go back and score ourselves, and we do that routinely. And so when we look at the hindcast record, Nino 3.4 has similar forecast skill to the relative index is similar forecast skill to the traditional. And as I'm going to show you in the last 10 years, it seems to have smaller errors as well. Okay, there's a lot of plots here. I apologize. Top is the traditional Nino 3.4 skill. Reds is more skillful. I mean, these are large values around 0.9. This is showing different models from the North America multi-model ensemble. Target month, the month you are predicting, is on this axis, and the y-axis is lead time, so longer lead times toward the top. This area with the blues is essentially our spring predictability barrier where we see less skill. And so one of the messages I wanted you to see here is that these two plots are not wildly different. All right, the skill is roughly comparable when you're looking at the anomaly correlation. There are differences, and I'm showing the differences in the anomaly correlation at the bottom, but they're fairly small. This color bar goes up to 0.3. All right, so these are pretty small differences. We did a test to test the statistical significance of the difference, and the dots are showing where they are different. So not a lot of dots here. Where they occur tend to be at longer lead times and also for spring target months. So that is a deterministic metric. This is one way we grade our ENSO verification or ENSO predictions. This is a probabilistic metric. It's a reliability diagram. And the traditional measure of ONI is here in the top left. The relative measure is in bottom right. And in a reliability diagram, you basically want your lines, which represent El Nino, La Nina neutral, to hug this black line, because this black line is perfect reliability. What perfect reliability means is that your predicted probability, say 0.6, equals the actual historical probability. So in other words, when you tell your users there's a 60% chance of El Nino coming, every time you go back to your historical record, you look to see whether it actually happens 6 and 10 times. All right. So that's what the reliability plot is giving you. And quite honestly, this is pretty good reliability. Just in the traditional, we look at that and we go, not bad. Relative is even better, which really kind of surprised me. I showed this to my colleague, Mike Tippett, who is a real master of verification. And he immediately said it's probably cancellation of errors, which is it's a smart comment because the whole North American multi-model ensemble sort of works in this principle. That is, you average together all these models, and where you see real valid forecast signals, they'll agree and show up in the mean. And then where you see disagreement, you'll average it out. All right. So that works in the NME space. In the relative space, keep in mind we're subtracting out the tropical mean. All right. So tropical mean is another source of error. Right. There's going to be signals and noise in there too. So now you're subtracting out more, potentially more error. We need to look at this a little closer, but I think that's what's happening here and is why the reliability is improved. All right. So I looked at a deterministic metric over like a 40-year record, a probabilistic metric over a 40-year record. Now let's talk about what's happening right now, because we're seeing an offset here that is quite noticeable. And we've been watching this for the last year. We've been creating these diagrams and studying them. So this is on the left, the plume for from the NME, different lines here are different models. The dashed line is just a prior monthly initial condition. So this is January initial condition. The solid is February initial condition. That way we can kind of see how it's changing from month to month. And then here on the right is a relative. Again, these are the solid lines, February initial condition. And right now you see we're in our weak piddly La Nina from a traditional standpoint. And then we're very quickly expected to get to our minus 0.5 thresholds and we'll be in ENSO neutral. From a relative perspective, look at this. Almost all of these lines, not all of them, but almost all of them are below our La Nina thresholds. So that just stays in La Nina. We potentially have another second dip coming up next winter. So these are pretty different. I also want to credit the IRI data library. They're the ones who make this data available, easy to download and use, and you can do this on your own. So to emphasize, this is an amplitude offset, okay? So I was like, okay, well, I've looked at anomaly correlation, but what if I just look at error in that amplitude offset? So here I take looking at error, and by error, I mean forecast minus observations. And I want to know whether my error in the ONI is bigger than my error in the RONI, the relative index. And so I've done this for all start times going back to about 1980 to present. And where you see these red shading, that is where you have more error in the ONI. Okay, blue is more error in the relative index. And what you see is it kind of goes back and forth, particularly in the early part of the record. And then in the later part of the record, I'd argue, we're starting to see more reds, particularly in this period, which I'm going to zoom in on here. So it's the exact same data, but now zoomed in. And so arguably, I would say that these positive values, more error in the ONI is becoming more evident. And it ends, this time series ends with this particular most recent 12-month period, which is clearly better forecasted in using the relative index. Now, I should back up and mention that in, before this La Nina form, all the models were too cold, even in a relative space and a traditional, they were too cold. But what this is saying is that essentially, if you're using relative, it wouldn't have been as cold and it would have been a little bit more attuned to what happened in the observations. All right, this gets to our last point, and then we can stop and answer questions and have pizza. Sorry for the virtual folks. There's pizza here, but don't think about that. So we're seeing these large differences in the real-time record. And so here we have our ONI is the way CPC currently calculates it, minus the relative index, all right? And so the blue line again is the RONI, and then the red line is the ONI. We have this period right here, which is discernible to us, and this is the difference. All right, so we've seen in the last 10 years, these differences sometimes are up here around 0.4 degrees C, and then we get to this period where in the last year, year and a half, we've actually seen 0.5, 0.6 degrees C differences between these two index. This is big, guys, because keep in mind our thresholds for El Nino, La Nina are half a degree. And now we're seeing differences between these two indices that rival that. In fact, if you look at our most recent period here in NDJ, the ONI, the traditional value is at minus 0.5, so very weak marginal event here. And our relative index is minus 1. All right, it's a big difference. It's like a difference between like kind of a weak and moderate event. Okay, this is another way to look at this. Here, I'm looking at monthly Nino 3.4 values. I'm looking at the evolution. This is the traditional Nino 3.4. Bottom is the relative Nino 3.4. And I'm calculating all prior La Ninas going back to 1950. I'm color coding based on the strength. So if it's a weak or moderate La Nina or strong La Nina, you can see that here. The current evolution is this black line. And you see in the traditional, we just barely got below these thresholds to declare La Nina conditions. But if you look at the relative, look at that. We were probably in La Nina back in the summer. And now we see that it's actually down here more in like kind of a moderate strength episode. So again, these are large. You can zoom back out. So here, instead of doing the calculation in the index, I'm actually doing it by grid point. And this may not be quite kosher. Someone might flag this and say, maybe you shouldn't quite do this, but doing it anyway for now. The top one is traditional. Bottom is relative. And so here I'm doing this tropical mean subtraction at each grid point, and then I'm doing the rescaling at each grid point. And for the most recent period here, it's very clear that we have a more pronounced La Nina event. We see these nice tropical instability waves. I know this is a satellite-friendly group, so thank you for your work so we can see those tropical instability waves. And so ultimately, though, we have a much more significant La Nina. This is looking at Hofmallers of daily OISST version 2.1. And on the left is traditional calculation. On the right is relative calculation. And it's pretty different, right? I mean, we see our La Nina kind of emerge here toward late in the year in the traditional calculation, but in the relative, it's really astounding. You can see that really nice westward propagation and these tropical instability waves embedded in within. It's really kind of cool to look at. Okay, so these are the same plots you saw below or in prior slide. And so my message here is that simply, it's fine to use a real-time SST index, but it has to reflect the other aspects of the coupled ENSO system, all right? If it can't do that, then you have an issue. This is showing the Central Pacific OLR, and I will define that in the coming slides, but it's another measure of essentially a proxy for convection in the Central Pacific, right on the equator. And again, I'm showing all previous La Ninas. Black line is where we are now. And you see we're kind of in that upper tier of La Ninas when you look at this OLR data. This is looking at equatorial SOI. Again, I'll define that in the coming slides. But this evolution too is really top tier when you look at the equatorial SOI. We have fairly noticeable La Nina event. And so I'd argue these two atmospheric indicators are more aligned with the relative index than they are with the traditional. All right, final 2 slides and then we're done. So here I'm looking at the mean sea level pressure. I'm using ERA 5 data. I've also done this in CDAS, very similar. And so the equatorial southern oscillation index, for those aren't familiar, are just these 2 box regions in the Eastern Pacific and Indonesia. And what I do is I standardize each of these boxes, I subtract them, and then I standardize them again. Okay. And so it's essentially an on equatorial measure of the strength of the Walker circulation. All right. So this is what we've seen in the last season. Very consistent with La Nina. We have the higher pressures in the east and lower pressures over Indonesia. And here I'm showing 2 reconstructions. This is very simple. This is just a linear regression, and you weight it by the relative value and the traditional value. And when you weight it by the relative value, which we know it's stronger, you get this very distinctive La Nina-like dipole that rivals better the intensity of what we see in the observations. The traditional, not as much. And you can do this for all seasons. So you can create this equatorial SOI reconstruction. The orange is the relative reconstruction, the blue is the traditional, and then the black is the observation. So you can sit there and see how they all track each other. And again, it's over here in the recent records, I go, ooh, we might have an issue here. Because what we're seeing is the relative ONI reconstruction is hugging that black line, the observations, better than the traditional. And I can do a difference, right? I can look at the error. And here, what I mean by error is I'm taking the reconstruction minus the observations. And I'm saying is relative error bigger or smaller than the traditional error. Negative values here means that the relative reconstruction is doing better matching to the observations than the traditional. And you see some noise going back and forth. This is encouraging. This says that like we haven't been messing up really because the Nino traditional values have been pretty good. Again, I still like traditional or the relative method more because we can use that single climatology. We're not having to do this weird rolling thing that we do with our traditional ONI. But this is a different problem and it's something that is becoming a little bit more noticeable right now. This is Central Pacific OR. I'm using a University of Maryland data set. Yay. I was very proud to swap that in. I also did it in the CPC ones. They're pretty similar, so that's good. This is outgoing long wave radiation. And the Central Pacific ORs, it's very simple. It's just this box region here. And this is strongly correlated with Nino 3.4, which is how we identified it. So this is the observations. You see the suppressed convection near the dateline, enhanced over Indonesia, very La Nina-like. The reconstruction weighted by the relative value is, fairly noticeable. And then the bottom's the traditional and a lot weaker, right? So the relative, again, seems to be matching better what's happening. Do the same exercise where I have my time series, and then I look at the difference. And here again, just like in the equatorial SOI plot, we see these big differences where relative reconstruction is matching the observations better than traditional. We also, this is not in the equatorial SOI plot, like this period here in the 90s, right here, shows up right here. So this is interesting to me. And I looked at it and I went, this is interesting, but I don't have time to investigate. So I'm going to give it to you all because you're the satellite experts. But this is suspicious to me because this occurs during a rather major El Nino event back in the 90s, 91, 92, I think. And so what this is saying is the relative index was doing a better job. And I wonder to what extent the Pinatubo eruption may have influenced the traditional values to the point where the relative was actually capturing ENSO variability better. But I don't know OR data, so I'm going to give that to you guys. All right. And that brings us to a final slide. This just kind of repeats what I've been saying and makes the argument for relative SSTs. It's not perfect. No index is perfect. But I would argue that we're seeing some fundamental issues here with the traditional, and also the traditional is just a little clunky with this again, 30-year moving period. So and become a fan of this. Relative only link is here at the bottom. We monitor at CPC. It updates every month. And then there's GitHub code as well. If you can't find it, I can send you the link. Just email me. All right. And that brings me to the end. I really appreciate the opportunity to talk to you all. And I'll go ahead and open this up for questions.
Any questions? Maybe we can start with in-person questions. Thanks.
Hi.
Disclosure, I wear hearing aids, and the audio from the Zoom may come out a little garbled here in the room. So I'm actually gonna, if you can drop it into the box, that'd be great, because then I can read your question, which is just makes things easier. If you're in the room, I can hear you, because I can just walk right up to you and be like, hey.
Thanks so much for the talk. I'm wondering if you've looked into how the global teleconnections respond to relative ONI versus traditional ONI. So I would imagine they respond better to like the full fields, like sea surface temperature, and that's always bothered me. So
Yeah, it's a really good question. Yeah, so when we sat down and looked at this for the journal climate paper, there is some analysis that focuses on the teleconnections. But one thing I kind of came away with in that analysis is that the relative index is better in certain seasons and certain regions when you look at correlation across the globe, but not all seasons and not all locations. And part of that, I think, is because these two time series are super correlated. So you're seeing these little jumps. So I kind of want to go back and look at this, because I think we're starting to see these offsets in the air, and that might become more a problem for assessments of teleconnections. I didn't have time to get into this, but I have a colleague, and I really want to advertise some of his work, because he's been doing some really interesting work. So I'm part of the ENSO blog, which is this climate.gov update on El Nino and La Nina, updates twice a month. We've been doing it for 10 years. It's a great crew. And we can kind of talk a little bit more about these issues that crop up. And so what he did is that he looked at the predictions. So he's only in the model world for precipitation over the United States. This is Nat Johnson. He's a blogger. He's at NOAA GFDL. He looked at predictions of the winter. And what he noticed, I'm just going to quickly move this. He noticed that if you do the reconstruction in the prediction space based on the traditional index and the relative index amplitudes match better with what the model's own prediction is showing. So that's really interesting, because that implies that the relative index in the model world is actually getting the intensity of this. Now, the subtle argument here is it's in the model world, because in the model world, you can kind of tease out the signals from the noise the better. Observations will tell a different story, and we know that, because there's a lot more noise when you actually look at the forecast relative to the observations. So it won't be as clean when we go back and look at this, and Nat has a plan to do this in our blog. But it gives you an idea of how these offsets may actually be impacting our assessments of the teleconnections. Great question.
thank you.
And I want to make sure I give opportunity. Okay, no sound, no sound, no sound. Yeah. Yeah, so this is interesting. There's a reference here to other ways to remove these sort of trend errors. And there are, there is actually some work by some folks in Singapore that looking at some adjustment in the trend index and using that in real time. And it's decent. I mean, I would say, that works to an extent. It does assume certain things. Again, what I like about this is physically based. We're not making a lot of assumptions. So in that when you do it in the statistical space, you have to pick a start period. You have to assume a certain curve fit. You have to assume the future is going to fit that curve fit. And these are all these are assumptions. And so, you know, while they may give you an answer similar to what we're achieving now, I think that the simplicity and the physical rudeness of this index are its advantages. Okay. All right. Any other questions from online? If you want to drop them into the box. Oh, here we go. I also want to be respectful of people in the room, but we can talk while we're eating pizza. So that's our advantage. All right. So can the RONI better capture ENSO events that aren't centered? How do I get rid of that? What is this thing? Oh, there. Oh my God, that's annoying. Okay, there we go. Can the RONI better capture ENSO events that aren't centered in 3.4 box like Modoki or Central Pacific ENSO events? All right, really, really good question. So far our studies have focused on Nino 3.4, and that's because I come from CPC and this is our official index. I have not looked closely at these other regions. It's worth doing and exploring. I do think the physical constraints here would apply to these other regions. I don't see an obvious reasons why they wouldn't, but they probably should be looked at a little closer. In fact, I have a colleague in Peru, Ken Takahashi, who has been looking at changing their coastal El Nino index in a way that would be more relative. So he has a prototype for a relative coastal El Nino index. So already there's a little bit of work in our community to explore how we can apply this idea to other regions. Great question. All right. Anyone else? Go ahead. Yeah.
Hi, great talk. Thank you. I was just wondering if you had any kind of speculation on why the difference between the traditional and relative index has become so pronounced over the past year. And then maybe follow up, given that that is what you're seeing, what do you think about, I mean, or what is the plan for maybe switching over to the relative index as the primary ENSO index at CPC?
Yeah. So those are really good questions. So I also have that concern. I'm like, why is this happening? And why is it so pronounced over the last year? This also comes roughly at the same time we've seen just this all over warming in the global oceans. So to me, is that a coincidence? Maybe not. So maybe the answer to this is tied up in that answer as well. So there's clearly been, I mean, for the easy answer is that we're subtracting out tropical mean, and tropical mean is warmer. That's why. But it doesn't really get at, you know, why the tropical mean has been so warm, and, you know, would we expect that to continue? There's also the fact that our climatology is now this 1991-2020, and we're sitting here in 2025. So maybe there's an element of our climatology just getting really stale and not taking in account what we're actually seeing in terms of these offsets. So it's a great question. Oh, and you asked, sorry, second question was, you know, to what extent are we considering this for our operations? We are. You know, there are internal conversations going on right now, nothing serious, but potentially we may, you know, if the policy structures are interested in this, we may look into making this a more official index. To be clear, I mean, the government, we move slow. We're not going to like flip a switch and, you know, next week for sure. So this will be a very deliberative process where there'll be a comment period. And then down the road, even then, if we decide after the comment period to adopt it, there will be a period of transition. So there'll be several months where we're just kind of transitioning. And we're not going to like rip out the traditional value and say, don't look at it anymore. We'll probably have that as well. It's just a question of our declarations and our historical record, what we should be using here. So we're also, again, because I'm that middle manager for ENSO, we're trying to give the science community a little bit of time to catch up to this as well. So one of the reasons I'm here and I'm grateful for the seminar is that hopefully we're advertising this. Everyone should be exploring this. All right, great.
Thank you.
Okay, so any other questions? Feel free to interrupt me, but if not, let's conclude the seminar and let's give one more applause to the speaker. And thank you for attending
Thank you
our
very much.
seminar, and to the
John.
to the virtual attendees, we have more virtual seminars coming up. So please stay tuned. Thank you so much.
Thank you very much. I appreciate to the virtual folks for joining in as well. Really thankful.